Welcome back to Sustainability Ventures, where we go beyond the headlines and unpack the real environmental math behind the green transition. Today's topic challenges a popular assumption. Recycling batteries is always cleaner than mining new materials. It sounds obvious, right? Recycling equals sustainability. But what if, in some cases, the recycling process itself consumes more energy, emits more carbon, and creates more chemical waste than mining? As electric vehicles scale globally, as lithium-ion batteries power everything from cars to grid storage, battery recycling is being promoted as the environmental solution. But here's the uncomfortable question. Are some recycling processes actually more environmentally intensive than the mining they're meant to replace? Let's break it down. Lithium-ion batteries rely on critical materials: lithium, nickel, cobalt, manganese, and graphite. Mining these materials has well-known environmental costs: land disturbance, water usage, energy-intensive refining, and chemical leaching. So recycling seems like the perfect circular solution. Instead of digging more mines, we recover metals from used batteries and reuse them. The logic is strong: lower resource extraction, reduced geopolitical dependency, less landfill waste, lower life cycle emissions. And governments across the EU, US, and Asia are investing heavily in recycling infrastructure. But here's where complexity begins. There are three main recycling methods. 1. Pyrometallurgical recycling. Batteries are incinerated in high-temperature furnaces, often exceeding 1400 degrees Celsius. Metals are melted and separated. 2. Hydrometallurgical recycling. Batteries are shredded and treated with strong acids and solvents to dissolve and extract metals. And 3. Direct recycling, an emerging method. Attempts to preserve cathode structure with less chemical reprocessing. Now here's the key issue. The most common large-scale method today? High-temperature pyrometallurgy. And that process is extremely energy-intensive. Running massive furnaces at ultra-high temperatures requires significant electricity or fossil fuels. In some regions, that energy still comes from coal or natural gas. Let's compare energy intensity. Mining operations require excavation equipment, crushing and grinding, chemical refining. But pyrometallurgical recycling requires battery pre-processing, high-temperature smelting, and additional refining to restore battery-grade purity. In many cases, recycling facilities consume energy comparable to or exceeding primary metal smelting operations. If the electricity grid is carbon-intensive, recycling can carry a surprisingly large carbon footprint. And here's the twist. Some battery chemistries, especially newer low-cobalt chemistries, contain lower concentrations of valuable metals, meaning more material must be processed to recover less valuable output. That increases environmental intensity per kilogram recovered. Hydrometallurgical recycling avoids extreme heat, but introduces another challenge: chemical use. Strong acids like sulfuric acid and hydrochloric acid are used to dissolve battery materials. This generates toxic liquid waste streams, sludge residues, and heavy metal contamination risks. If not treated perfectly, these chemicals can create secondary pollution. In regions with weaker environmental enforcement, improper disposal becomes a serious risk. Ironically, a process meant to reduce mining damage can replicate some of mining's chemical hazards. Another overlooked factor: battery collection and transport. Used EV batteries are heavy, hazardous, and classified as dangerous goods. They require special packaging, handling, and long-distance transport to centralized recycling facilities. In many cases, batteries are shipped across continents. That adds transport emissions, fire risk, and additional processing stages. Mining happens once at the source. Recycling requires collection, transport, disassembly, processing, and refining. Each step carries environmental cost. At Sustainability Ventures, we believe in data, not slogans. Battery recycling is essential for a circular economy, but it's not automatically environmentally superior in every case. The real question isn't mining or recycling, it's how do we design recycling systems that truly reduce impact? Because in the clean energy transition, technology alone doesn't guarantee sustainability. Process design does. So here's my question for you. Should governments require full life cycle environmental audits before approving battery recycling subsidies? If you found this breakdown valuable, like, subscribe, and share this with someone who believes recycling automatically equals zero impact. Because in the clean energy transition, circular only works if the circle is actually clean.